source manufacturing.
Hello, friends. It's good to see you all again. I am Machinist. This is not my first LayerOne talk. It's not my third LayerOne talk. In fact, I've been coming here speaking for more than a decade now. So if you recognize my face, you sort of have an idea of the things I'm into. I have a background in machine shop. I do manufacturing here at the Jack Parsons lab locally. And I live out in the woods, in the wilderness. So interesting thing happened last year. Wifey comes up into the bedroom about 11 p.m. She's like, hey, there's a crazy noise downstairs and there's a bear like trying to come in through the kitchen window. By the time I run down there, the bear had already been startled off, but it was trying to figure out how to get in through the back screen door, like smash down a big glass door. And it just boggles my mind to think about how bad the situation is once the bear is inside your house. So I thought for a second, I was like, maybe we should sort of like ramp up our home defense abilities here. A few years ago, I gave a talk called Swords to Plowshares, where we looked at what was called a ghost gunner, a desktop CNC machine that had one purpose, just to make parts for firearms. And my talk was demonstrating how to use this machine as a general purpose machine to make whatever you want. Now we're going the other way back. We're taking general purpose machines and making self-defense items. So artist interpretation of what my evening was about to look like there. And what do you do in this situation? You defend yourself. Oh no, misfire. All right, cool, live demo. This is exactly what I wanted to happen. So I didn't actually make this device perfectly, but I know how it fails. So we're going to quickly embarrass myself and make this work. Repeating, ideally. All right, we have prevented a bear attack. Cool. So what gives me any authority to talk about this technology? Well, I do 3D printing for a day job, and my prints are a little bit better than normal. Up here, a couple of interesting examples on the left-hand side. That's the Cadre rover. That's the next one that's taking a trip to the moon. I 3D printed its clean room shoes. Those are made out of ESD safe PET G. On the other side over here, we have the EELS robot that was meant to explore the ice moon of Enceladus, the moon of Saturn, and it has like a ice covering with a liquid water ocean underneath. And the robot was meant to sort of traverse down in through the vents and discover whatever was meant to be down there. One interesting thing about the science robotics robot, if you look really, really closely, you can see my handwriting on one of those screws. So kind of neat to see the work getting popularized like this. So I already explained what we're talking about. We're going to use FDM 3D printers and modern 3D CAD tools to develop our physical parts and create them in reality. My weapon of choice here were Prusa 3D printers. They're pretty much like the Honda Civic of 3D printers. What the Prusas really did was allow the industry to sort of like solidify on a form factor. And the one thing that these things really changed the industry with is the flexible, replaceable build plates. They have a coating of Ultem or polyether imide plastic, which is it's adhesive to other plastics when it's hot. So it basically changed the methodology of 3D printing from needing to put down like blue painter's tape or a disappearing glue on the build plates. Instead, they just build right on top of this plastic plate and snap right off and you're ready to move on. So game changing. Everybody in the industry basically shifted towards this design because of the open source push. So what did I make? This design's called the Sliding Legolini. It was inspired by Jorg Spray. If you ever see the Slingshot Channel guy on YouTube, the big boisterous German guy, Yeah, so it wasn't his specific design. Someone else saw what he did and built the 3D CAD and released the files for free online. So crossbows were a particular focus here because, being around 3D printers, you hear people talking about, oh, I got a Liberator, I want to 3D print some guns. And it's always a bad idea for a number of reasons, mostly because it's so heavily scrutinized by law enforcement. And it just so happens that crossbows are pretty much carte blanche in California. The one complication is when you're during hunting season, you want to have a crossbow with a 125-pound draw. So probably not something you could pull by hand, but that also probably precludes anything being repeatable. In this instance, we're probably only putting out about 10 joules of energy, maybe a 30 or 40-pound draw. So we're not off by an order of magnitude in the power. We're off by a factor of 2 or 3, and we could easily update this design to have a stronger pull, a more forceful bow, a more forceful action. Oop. Okay, so why not this firearm? Well, these are particularly bad in U.S. law at the moment. Everybody's kind of scared of the black things. There's a lot of naughty features that you're not allowed to have in California. You can't test this at home. That was another thing, right? Like once I built the slingshot, it was like 2 a.m. and I cycled about 200 rounds through it, and the children were sleeping in the other room. Obviously doesn't bother them, right? That's no report is probably the way you want to be dealing with these kinds of problems, right? Because you hear a loud blam and like the entire neighborhood knows what just happened in your house. But when you think about it, what is the fundamental difference between a 3D printed crossbow and a 3D printed firearm? A little bit of force, a couple metal parts, but essentially it's the same. Plastic, some nuts and bolts, and a little bit of fitment. So here's the inspiration for the sliding Legolini. This guy is a hoot if you aren't familiar with him. There's several designs on the website where I got this for either the small handheld crossbow. There's a form that looks like a pistol, and then there's the full size, what's it called, the sliding instant Legolas, where he's got a compound bow with a magazine, and you can let off 5 rounds completely unskilled within several seconds. So this guy's up to some cool stuff. So when you look through the design files for either the Legolini or any of the 3D printed guns, there's usually a help file that's describing the process, and they're always completely off from reality. If you use 3D printers, you're probably using PLA filament because it's easy, it forms nice shapes, but the problem is not only is it brittle, but it has a really low heat deflection temperature. A 3D printed part made out of PLA won't survive a hot day on your car dashboard. It'll just completely melt. About 45 Celsius, they start to give out. Once you start talking about other polymers that are a bit more performant, PETG is my go-to. That's about 95% of what I use in my 3D print lab. If you need something crazier, we usually go towards carbon fiber or glass-filled nylon. Has a much higher heat deflection temperature. It's also just tough. It's not strong and rigid, but it's really abrasion resistant. So there's a couple of components on this which were made out of carbon fiber nylon, mostly the little locking parts, anything that had a lot of force on it. You see in the facts for the 3D print guns, oh yeah, if you can make the trigger parts out of metal, please do. Anybody who's ever worked with 3D printed parts under load or some functional things know that when they fail catastrophically, right? So, carbon fiber nylon, mostly PETG. I can't say I've ever been disappointed with a PETG print. Another thing that you notice in those facts is they always describe the infill rating at 100%, and 100% actually overloads the interior of your 3D printed part. About 80% infill is nominally solid, but 40% seems to be like the high limit of functionality. Any more than that, you're just adding mass without adding any extra strength. And the low limit for infill seems to be about 15%. Any less than that, and horizontal walls, ceilings and roofs or whatever, they start to sag because of the gap between any like infill components. The one thing I push all the engineers using these 3D printers is that thicker layer lines are stronger. Often I'll see people print the finest layer lines that they possibly can with the excuse that they're more accurate. And that's not true. The XY resolution of the printer will always be the same, whether it's thin layers or thick layers. It's the Z increment that changes with the layer height. So it's totally possible with a small layer height or a thick layer height that you end up with the same Z height because of the way the value is incremented. That being said, something that you want to consider is anytime there's an overhang that you're supporting, the overhangs tend to sag a layer or two. So when you have a 3D printed, or when you have a 3D design, when you have two parts that are fitting together, you usually want to offset the lines of the mating parts a little bit. That's what you would call tolerance. If they're not offset at all, you would call that line to line, and that's always poor engineering, because the moment you try and fit two things together, they don't go together. So tolerance, how much tolerance is about right? Rule of thumb is plus or minus 0.005 of an inch, plus or minus 125 microns. It's about the thickness of a sheet of paper, plus or minus. Anytime you design parts like that, they'll generally fit together. They'll generally fit right the first time, only requiring a little bit of final fitment. Another thing to consider is making all these parts on the same machine. Each machine's going to have a slightly different calibration. I've seen people go as crazy as like trying to calibrate the E-steps through the extruder to make sure that like the diameter of your filament is being accommodated for through your 3D print. I've never gone to that point of complication. Just adding a little bit of tolerance, knowing which direction you're trying to push these values, your parts go together the way you expect them to. So infill pattern does make a difference in the planar orientation of strength. So depending on if you're trying to put the strength of your part through one direction, or if you're trying to keep it isotropically all throughout the part, will determine what kind of infill pattern is best. Gyroid infill patterns, the infinitely wavy ones, tend to be isotropically strong in all directions. When I'm trying to isolate my strength along the Z direction, I tend to go for hex fill or triangular fill. Something I've been using these 3D printed parts for an awful lot is vice fixturing for CNC milling. So instead of making a complex shape set of jaws to hold a weird part, I'll just 3D print something, and that's generally enough strength to hold a part strong enough in a CNC mill to do any final operations. I've had them fail. They do fail. They're not optimal for every situation, but it is a quick workaround, saves you a lot of trouble just being able to go straight to the machine that way. So supporting your part has changed within the last year or two. Some new algorithms have been developed where when you had overhangs from your 3D printed parts, it would build up a series of straight lines from the bed or any features underneath. And anytime you have supports touching your part, it leaves a little bit of a scar. And when you're trying to fit parts very precisely like you would the sliding mechanisms here, those scars tend to take up more of that gap than your tolerance will allow. So new algorithms have been developed to create what's called tree supports or organic supports. And I wish I'll pull up some pictures later when we do some more live demos, but what they sort of like form organically, and I use those supports all the time because they tend not to scar the parts. You can have really complex geometries that, using old techniques, you would have been fighting for days trying to remove all the scarring, and now the supports just come right off of the material. It's fantastic. So Prusa Slicer is my jam. Why do I like Prusa Slicer so much? Well, again, it's like your Honda Civic, right? There's 10 million users out there. They're using it all day long, and it's just really well developed. All of the main branches of 3D printer slicers pretty much look back on Prusa Slicer for their basis. Orca Slicer is another open source version out there that uses Prusa Slicer code. The Bamboo Studio uses Prusa Slicer code. So obviously they're doing something right if everybody's using their code base to build all of their new works from. Another interesting change that's happened with all of these slicing softwares recently is now they accept step files. So throughout the history of 3D printing, the usual file format was STL, stereolithography. It's basically a mesh of points in 3D space with lines drawn between them. The problem with that is you can have a valid STL, which doesn't make a watertight shape, right? You can have just little points floating out in space, little lines floating out in space, and that used to make your slicer software like fall on its face and shit the bed. Nowadays, it's a little more tolerant of messy, non-watertight structures, but the big change in the last year or two is that all these slicers now use step files. So what's the difference between a step file and an STL file? STL files do not render curves. They render a sequence of straight lines, where the step file will actually generate the curve. So what does this mean for your 3D print? If you've ever 3D print off of a coarse STL file, you'll notice your round shapes are now tessellated. You now have an octagon. And if you're trying to get that plus or minus 5 thou fit, some of those straight lines don't fit anymore. Well, using a step file, you have the native curve, and the slicer software ends up tessellating it into tiny little points, but you basically can't tell the difference between the pure curves that the STL forms and the tessellation that your 3D printer will create based on that. So step files are a game changer with the file format that you're able to use in these. Another very powerful tool, which recently released version 1.0, is FreeCAD. My background's all in SolidWorks, so I have a pretty deep familiarity with what I expect out of the software, what it can do. And after poking around at FreeCAD recently, I am impressed with how well developed it is. I can't say I put 400 hours into it and can tell you like a statistical difference between the bugs in SolidWorks and the bugs in FreeCAD. But as far as like being able to pull up a complex assembly of parts, disassemble it, look inside, and isolate single parts and start making changes to them, like all of that functionality is available. It works. So like, sure, you could use Onshape or Fusion 360, all your cloud CAD that works really good and it's nicely polished, but not sometimes you might want to be like keeping your file types and formats and information to yourself, and that's what FreeCAD allows you to do. No more cloud, right? One interesting thing that you can use FreeCAD for is when you look at McMaster-Carr, all of their parts have CAD downloads. So you can take a McMaster-Carr part, change it to the way you want, and then 3D print it, right? Like they don't. I did this recently for a set of plastic hinges. Someone wanted me to make a box, but the leaves on the hinge weren't long enough. So open up the part in FreeCAD, start manipulating, adding some geometry, and suddenly now it's my customized part, but it's got all the hinge mechanisms and it print the first time the way I expect it to. We even got some kudos from the engineer who wanted it. Like, oh, this is way better than I was expecting. So how hard was this thing to build? It was effortless. Like, there were some video instructions, not really like a long extended PDF, but I basically treated this like IKEA parts, right? Like, manual, what's that? Start putting things together. Found a couple of weird, I guess specifically with this, all of the STL files were unoriented. So I print a few of them, and like the grip here is a good example. You can't really see, but there's a surface here which is really scarred, really messy. It's because it was a low incidence angle. It still had support, but because of the low angle, the support didn't really function very well. So it caused the edge of the handle here to be quite rough up against your hand. Another example is on the grip right here. The grip was actually print with the main face here up against the build plate. But what happens on that very first layer is the 3D printer is trying to squish that first layer in. So there's an artifact called elephant's foot. It actually pushes the first couple of layers out. There's a switch you can flip inside the slicer software. Say, okay, compensate for the elephant's foot and move that first value in a little bit. It's something you have to do a little bit of trial and error with, but I'm just pointing this out because I noticed an ergonomic error that wasn't in the CAD. It only shows up once you manifest this in reality. So yeah, about 48 hours of print time. The 3D print filament is extraordinarily cheap. It's about 2 cents a gram. But when you're estimating working on these kinds of projects, there's something called Hofstadter's law. A task of sufficient complexity will always take longer than you think, even when you account for Hofstadter's law. There's some rules about building spacecraft, and when you're estimating your time and effort, you want to multiply your effort by pi and move the decimal place on your cost, and you'll pretty much hit the target. So I didn't have all of the materials that I would have liked to build this. I think initially the rubber parts here were meant to be tube rather than band, but I scratched my head about that for about 10 minutes and figured out how to make that work. Another thing that I noticed after shooting a couple hundred rounds through this was the Kevlar strand here that interfaces with the bolt was starting to become abraded from traveling up and down this gap. So I had to add some serving, a wrap of monofilament fishing line around there to prevent any further abrasion. That's a pretty standard part for bows and arrows. I've never heard of that phrase before. Okay, so we talked about some fit and finish. That's just a part of the process of 3D printing. Usually your first one sucks, your second one's a little better, and you figured it out by the third try. There are provisions in the magazine here to handle broadhead bolts. So I bet those would poke a pretty nice hole into something, especially if I doubled the draw pressure. One interesting tidbit about this device, it is technically not a crossbow. Crossbow is one that when you pull it, it stays locked in its drawn position, where because this doesn't stay locked in its drawn position, it's technically called a sling bow. So like even lower threat as far as like, oh, that's a naughty device. Any firearm enthusiasts? Anybody? Couple? So surely you've seen the FGC-9 Yeah, wow, that was about what I was contemplating printing that and presenting on that device, but like I said, I can't really test it, can't really show you guys. I don't even trust all of you guys enough to show you that kind of a naughty thing, but I figured this was a nice compromise. But there's tons of development on the FGC9, lots of different models, of varying degrees of intellectual assembly, but it seems like if you pick and choose a couple of the parts here from a different design is called the Nutty. It's made out of like hardware store parts, a little easier to assemble than like welding bolts together. Some changes on the firing pin have been noted that there's failures in a smaller design. So the Partisan design has a more impressive firing pin. The Stingray is like a rifle form, so probably a little more California legal. And if you're going to look at these files, get them from Odyssey, not from FOSSCAD or DefCAD, because those are probably FBI plants, and yeah, you don't want to end up on those lists. All right, I guess we got some time for a live demo. Any questions so far while I spool this up? Yes, sir. So the question was, what was the time frame from the bear encounter to having this in my hands? Better part of a year. So the bear problem in my town was, let's say, notorious. Like, I grew up in the mountains. I've seen a couple of bears, but like walking around the neighborhood when I first moved up there, I see like people have like the electric fences across their door. You know, that strikes me as a little unusual in bear territory. And sure enough, there were a couple of overzealous bears that were hanging around the trash transfer site in town. But apparently not long after my encounter last year, the bears got relocated out of town. It was a mama bear and a couple little cubs. So the worst possible scenario you could have, right? Did I ever measure the velocity? No, I didn't. I don't have the tools for that. I don't know. What do you think the velocity is here? I don't know, 100 feet a second? Any CAD users in the building? Sorta? Yes. Can I show you what that's on my desktop? Oh, the Sonic. Okay, yeah. Sanic. So for some reason, this first load is always a little delayed. Let's see if we can pull up Crusoe Slicer. All right, I'll show you a couple neat tricks in Crusoe Slicer. So here's how you import quickly. We've got all of our STLs. Control A. All right. Okay, so it's a big mess right now, but this will automatically arrange all your parts, create all the extra build trays if necessary, and then it's just up to the human to determine the orientation. There was one part here that was a slightly larger form factor than the Prusa build plate, and no matter what orientation, I couldn't quite fit it on there, so that's the one that got to print on the fancy Mark Forge. But in my experience, the Prusa prints are every bit as precise as the ones we print on the Mark Forged. You can even print the same material through the Prusas. It just helps to have an enclosure and a hardened nozzle because the carbon fiber material tends to be really abrasive. Oh, I wanted to show you some tree supports. Okay, so I only touch about maybe a dozen buttons in everything in here. So generate support, organic supports, and support on build plate only. That one's important. If you neglect to do that, your print will generally fail. I've just noticed that when supports are built on already deposited model, it doesn't tend to stick very well. And there's our tree supports. And 93 cents a filament. So just to give you an idea of the economics, the tool flow. Cool. All right, cool. FreeCAD shows up. And this is a very familiar interface if you're used to modern CAD. Transform. One thing I would recommend for doing some power CAD use is getting a 3D mouse, because it just makes the navigation way easier. Not a lot of contrast here, but just sort of gives you an idea of what you're looking at. If we want to save a single part, actually you would export as not 3MF, but as a step file. Okay, so this is the upper receiver. Now let's see what Prusa Slicer thinks about it. There's your naughty part. And 12 hours of printing for $4 of material. So outrageously economical to use this tool, but it requires a few sets of software tools and understanding of the tool chain to really like make use of it. So that's what I'm trying to encourage you guys to do is like, in the 10 years I've been doing this, like the software tool chains have changed dramatically, right? Like when I started, there was basically no CAD options available unless you were funded by a corporation, right? Every seat of SolidWorks is like $4,000. Talking about NX, it's like $40,000. So nowadays, like CAD is ubiquitous. There's several cloudy online options you can use for free. There's this stuff that's outrageously powerful, but there's just a little bit of a learning curve. However, all CAD is essentially the same. You have a sketch, you turn a sketch into a three-dimensional part, and you do something with that. I haven't been doing any drawings. There's a bunch of segments of SolidWorks that I'm not really familiar with, but when it comes to like mechanical fabrication, just being able to analyze a part, being able to modify a part, and then export the part. That's really the tool chain that's improved dramatically, giving you lots of options. What's also interesting is right in the slicer, it gives you lots of abilities to modify your part. So that's been one of the challenges dealing with STL files versus step files. Is STL to step is the same comparison as raster to vector. You can go one direction, but it's really hard to go the other direction. If somebody hands you an STL file, you're like, what the hell am I going to do with this? Like SolidWorks doesn't want anything to do with this. The file format's all wrong. It's really hard to make modifications to this. But there are a couple of shortcuts inside of the slicer. So what we can do here is we'll add an SVG modifier. So we can add a random SVG to a curved surface of the part. And let's cut 10 millimeters. Okay. So when we reslice this, we should expect to see our changes. So what we're doing is we're making the modifications to the STL, which just recently was prohibitively difficult. Now the slicer makes it effortless. You can just as easily wrap text around any of these surfaces, adding primitive shapes, combining, separating things. An operation that I do in here often is when you export a step file, often there's multiple bodies in the same part, and you need to be able to manipulate them and split them. You can do that all inside of the slicer software. Let's see. This one doesn't have extra parts, but this is the menu you would go to if you had combined parts and you wanted to manage them separately. So split two objects. Don't have an example handy. So I think I'm quickly coming to some conclusions here. Yes, because my last slide is questions. So I'll open up the floor for any questions. Anybody want to say anything? Yes, sir. So the question was, the explanation of STL files was helpful. How can you compare that to 3MF? So 3MF is like step file plus plus. It's the step file and sometimes a little bit of slicing information, but really you can think about it as just like the plate. Because you can change you can export 3MF between different slicers into SolidWorks or whatever, but it doesn't always have the slicing information. Some of that gets lost from application to application, but it's essentially the larger grouping of the STLs in whatever orientations you've determined. So that's a good question. The question was, what's the fundamental difference between using FDM versus resin printers? I've got a handful of resin printers at work. We've got the Formlabs printers. I hate them. I loathe those printers, mostly because there's more than an order of magnitude in cost difference, right? Like the resin printers, the resin can only sit in the tank for so long before it goes bad. The alcohol that you use to process it is constantly evaporating. Then when you dip the resin parts in the alcohol to get the extra resin off, now you're left with like toxic sludge. What do you do with that? It might be easy just to go dump it outside in your garden or whatever, but at a large government corporation, it's a nightmare to deal with that kind of stuff. So like the prints are easily double the quality, right? In terms of like resolution, in terms of like geometric fidelity, they're the same. I have some, if you're interested, I brought a part here, probably my favorite FDM printed part. And the guy I delivered it to said, I didn't even think this was FDM printable. And the FDM part ends up being $1. The resin part ends up being $50 once you like factor in all the overhead and actual effort you have to put into processing them, where the FDM parts are just immediately done. Any other questions? Yes. So how do the mechanical properties, how are they different? So a lot of that, we're discussing the mechanics of FDM parts, and in terms of like material properties versus the resin prints. So just between FDM to FDM, let's compare apples to apples right now. PLA parts, if I had a part this big and dropped it on the ground, it would shatter. That one's fine. So just it's not as rigid, but it's way more durable. It's tougher. The resin prints, they come, you can get resins all over the spectrum, from soft silicone-like resins to things that are like, it's effectively glass hard. So like the comparison isn't really direct. Once you're talking about the similar material properties, I can't say I've seen anything on a resin printer that outperformed an FDM print in such a mind-boggling way that was the only way to do it. Like, sure, some of the aesthetics are a little bit nicer. Sometimes you have, like an angled surface that, the tessellation is so small. You're like, oh, that's a little bit better. But it really comes down to aesthetics. The other problem, like I've been harping on, is anytime you have support structures and those surfaces that are attached to the support structures, whether they're FDM or SLA, you still end up fighting those surfaces, end up reorienting and reprinting your parts based on that. So there's a little bit of trial and error, but basically anytime you have like an important surface that needs to mate, needs to be precise, that's one I try and keep support away from. Anything else? Excellent. You guys have been great. Thank you. Hope to see you all at the LayerOne after party. And break.